I am Sadiq. My student ID is 2106142. Our project is an FPGA-based adaptive digital clock with temperature compensated drift correction. In most FPGA, crystal oscillators drift as temperature changes, causing timing errors over time. While hardware like TC Exos can fix this, they increase cost. Our goal is a fully digital firmware-only solution using the onboard XADC sensor, requiring no extra hardware. Our main objectives is to design a clock that automatically compensates for this drift. We use the Nexus S7's XADC sensor to monitor the die temperature every 100 milliseconds. By modeling the non-linear temperature frequency relationship, we aim to achieve ±1% correction accuracy across a wide temperature range of 20 to 80 degrees centigrade.
Assalamualaikum, I am Shihab. My student ID is 140. I am going to walk through the overall system architecture. The design is built around three main pipelines working together. On the left, we have the data acquisition stage. A hair dryer hits the FPGA board and the onboard XADC sensor reads the die temperature every 100 milliseconds. The temperature value is then fed into a drift correction stage where a lookup table maps each temperature to a corrected terminal count. This is stored in UQ 28.8 fixed point format. Finally, the corrected count drives the timing and display stage. The second generator counts to that corrected value instead of fixed 100 million. The timer counter tracks hour, minutes, second, and everything is multiplied onto the 7-segment display. The key insight here is that every module fits into the next. Real-time temperature directly controls how long 1 second actually is. Now zooming into the XADC module, this is Xilinx built-in 12-bit analog to digital converter. So we need no external sensor at all. The module uses DRP, Dynamic Reconfiguration Port interface, to poll the temperature register every 100 milliseconds. Internally, it runs a 4-state finite state machine. It starts idle, issues a read request, waits for the data ready signal, and then in the convert state, it applies the formula. ADC code times 503.975 divided by 4096 minus 237.5, giving us an integer Celsius value. We use a bit shift right instead of division, which keeps everything in integer arithmetic. No floating point hardware needed on the FPGA. The output temperature is clamped between 20 and 80 degrees Celsius and mapped into a 6-bit LUT index ranging from 0 to 60. Finally, a temperature valid pulse ensures downstream logic only updates when a fresh valid sample is available, preventing any stale data from propagating through systems.
I am Mahfouza Maisha, ID 2106143.
Before diving into how we have collected data, let me first explain why we need it experimentally in the first place. The core problem is that FPGA crystal oscillators don't drift in a perfectly predictable way. While we know theoretically that temperature causes frequency drift, we don't know the exact drift amount for a specific board. This is because every crystal is slightly different and has its own manufacturing tolerances. It expands or shrinks due to temperature change resulting in clock change. We have collected data experimentally by heating the Nexus A7 FPGA board gradually using a hairdryer from 30 degrees Celsius up to 70 degrees Celsius. Our data collection process followed a specific pipeline. First, the FPGA reads and syncs the temperature via the XADC sensor. Then the elapsed time is transmitted to the PC via UART. The PC captures this alongside the PC's own system time, while the FPGA simultaneously displays the hexadecimal drift value on the 7-segment display. Finally, these values are used to calculate the LUT table entries. One of the most exciting future directions is that replacing the fixed LUT-based approach with a machine learning model. Our current system is limited to one board and only 25 points for one calibration, but if we collect a much larger dataset across multiple FPGA boards, water temperature ranges, and varying operating conditions such as voltage and aging, we could train an ML model to learn the drift behavior automatically. A trained neural network could predict the corrected clock divider count in real time, adapting to conditions that a fixed LUT simply cannot handle. This could make the system truly adaptive rather than pre-calibrated and would generalize across different hardware without needing manual recalibration for each board. The table on the left shows that as temperature increases, the drift value also increases from 30 degrees Celsius to 70 degrees Celsius. The graph on the right plots the data with the temperature on the x-axis and drift in hexadecimal on the y-axis. We can clearly see that the curve bends upward and confirming the drift relationship is nonlinear. To model this nonlinear behavior, we have tried to curve phase in MATLAB using polyfit function. The left curve shows the linear feed and it doesn't follow the data well, especially at the lower and the upper temperature extremes. The right graph shows a quadratic feed of order 2 which matches the measured data very closely across the entire range. The derived drift equation is given. This quadratic model is what we use to build our recursion lookup table for the system for our 25 data point dataset.
I am Zarif Sher Ahmed, student ID 2106141. So the core problem we were solving here is the crystal oscillator on our Nexus A7 doesn't actually run at exactly 100 MHz. It drifts slightly depending on temperature. And if we are counting to 100 million to generate a 1 second tick, even a few ppm of drift will accumulate over time and our clock becomes inaccurate. To model the drift, we used a standard quadratic relationship. The fractional frequency error equals beta times t minus t naught squared, where t naught is 25 degrees centigrade, our reference temperature where the crystal is on spec. For example, at 40 degrees centigrade, we measured a drift of minus 7.875 from our hardware data. Plugging that in beta comes out to minus 0.035 ppm per degree centigrade squared. And you can see in the table, beta value stays very consistent across 38 to 41 degrees, which validates that our quadratic model is a good fit. Now from the ppm value, we compute a corrected terminal count, n corrected. Instead of counting to exactly 100 million at 40 degrees centigrade, we count this. And since our FPGA cannot do floating point, we store this as a UQ28.8 fixed point hex value. So the LUT in our Verilog is just a simple case statement. Temperature index goes in, pre-computed 36-bit hex value comes out. No runtime multiplication, no division, just a table lookup. Now for the display and status indicator, on the left you can see our 7-segment decoder table. This is a standard active low mapping for hex digits 0 through C with the segments ordering G, F, E, D, C, B, A. We use this to show the current temperature and hexadecimal drift values on the board's 4-digit display. So during our demo, you can physically see the FPGA reading is in real time. On the right is our LED indicator mapping, which acts as a live status dashboard. LED 7 down to 0 is the temperature in binary. This confirms XADC is working. LEDs 9 and 8 indicates which time field is currently being set, hours, minutes or seconds. LED 14 is our heartbeat. It blinks once per second. So if we see a steady 1 Hz blink, that confirms our compensated clock divider is generating the corrected 1 second period. And LED 15, it lights up when the user enters the time setting mode. So basically, just by looking at the board, we can verify the entire pipeline: temperature sensing, drift compensation and clock accuracy without needing any external debugging tools. Thank you.
Hi, I'm Tahir, my student ID 2106139, and now in the Vivado implementation section we can actually see that we had actually our main compensated clock, which was designed by this project Adaptive Clock Top. And in order to see the effect of the drift, we created another project which was compensated clock top. So here we made our clock with exaggerated drift. This is our demonstration. So here in the result and analysis section, by using this formula here, ppm is equals to n corrected minus n naught divided by n naught into 10 to the power 6, we measured the values of ppm for different temperatures. And now the main limitations of our project was that the temperature was controlled via a hairdryer, which was not a calibrated chamber. So our measurement was quite noisy. We couldn't keep our temperature constant for a long time, and the temperature up and down was unsteady. And the LUT lookup table we found was only for 20 degrees Celsius to 80 degrees Celsius, and we only used one board to test, so no cross device validation was in our project. So our future work should be that if we can actually replace our hairdryer with a calibrated temperature chamber, that would give us a steady temperature which can be kept at a constant temperature for our desired time period, and we can extend the lookup table range beyond 80 degrees Celsius for industrial use. We can add NTP sync for calendar accurate timekeeping, and also if we could actually use multiple FPGA boards for consistency to prove that our project works for different FPGA boards as usual. And obviously reduced polling interval for faster thermal response should give us an more accurate result. So, and this is the end of our slide, so thank you.
So now what we are doing is we are collecting the data
in the leftmost two digit that we can see the temperature is being varied by the hair dryer, and on the right we can see the drift. So when the temperature rises, we can see some different values of drift. These data will eventually give our model. So so if we plot drift versus temperature graph, we can actually fit a model which we actually created. And here you can see the temperature is constantly rising, and their corresponding drift are being recorded. So here it is a normal uncompensated digital clock. So if the FPGA always counts to 100 mega cycles, then its second is increased by 1, it is basically an uncompensated clock, because here whatever the temperature is, the clock always counts up to 100 mega cycles instead of counting up to the corrected count which we have in our lookup table. So it is basically an uncompensated digital clock. Here we cannot actually see any time difference. The time difference that we are seeing between the mobile screen and the FPGA is basically human error. The main issue is the drift is so less, so we cannot actually detect with our open eyes. So in this video we can actually see when the temperature rises, the clock counts faster and faster. So we are actually trying to see the effect of drift here. So the compensated logic is to match a temperature with its corrected count. So let's say when we have temperature 40 degree Celsius, we have corrected count 50 less than the 100 megahertz original. But this is not actually, we cannot actually see or tell a difference between our original count, actual count, and FPGA count in our open eyes. So what we have done here, we have multiplied our drift by 10,000, and now we can see that the temperature is, when the temperature rises rapidly, the clock also counts more faster and faster. So it's basically, and give us an idea that in the long run, say for days and week, actually we can, the temperature effect will actually be there in the FPGA if we don't use a compensated clock.